Okay, let's think about something simple. Imagine a kid, right? Trying to figure out which two trees are furthest apart so they can set up a race start and finish line.
Yeah, they'd naturally look at the distances between all the different pairs of trees, wouldn't they?
Exactly. Or like someone reading a murder mystery. They're constantly connecting clues, figuring out how one piece relates to another.
Uh-huh. That core skill,
Yeah.
understanding how things connect and interact. That's what we mean by relational reasoning. It's just fundamental to how we think.
It really is. But here's the tricky part. While we humans do it almost without thinking, getting AI, especially neural networks, to do the same thing, that's been a real challenge.
Yeah, it has. Older symbolic AI tried, but it often needed relationships to find up front, which isn't great for messy, real-world stuff.
Right. And deep learning, great at spotting patterns, like finding a cat in a photo.
For sure. But figuring out the relationship is the cat under the table. Is it chasing something? That's where it often kind of struggles. The connection is the hard part.
Precisely. Those subtle but crucial relationships. But that brings us to today's topic, which is really promising: relation networks, or RNs.
Relation networks.
Yeah, think of them as, well, the paper calls them a simple plug-and-play module. Basically an add-on to help neural nets get better at this relational reasoning stuff.
Okay, so it's a potential solution. And connecting this back, the paper we're looking at, a simple neural network module for relational reasoning, really dives into this.
Right. So our mission today is to explore how these RNs actually work and, what they're capable of based on this research.
And others really put them through their paces. They tested RNs on visual question answering, text-based questions, even understand it like simulated physical systems. A good range.
Sounds good. So let's get into it. What exactly are these relation networks? What's the core idea behind them?
Okay, so at their heart, RNs are basically building blocks for neural networks that are explicitly designed to focus on relationships between things.
So it's built into their design philosophy.
Exactly. Kind of like how CNNs are structured for spatial stuff in images, seeing patterns, or RNNs for sequences, like words in a sentence.
Uh-huh.
RNs are meant to do that same kind of specialized job, but for relations. They want to bake that capability right in.
Okay, baking it in. How does that work mechanically? Is there like a formula?
Yeah, there is. It looks a bit mathy at first, but the idea is pretty intuitive. If you have a set of objects, let's call it O, where each object O is like a description.
Okay, like features of the object.
Right, feature vectors. The formula is RNO equals FE of the sum of theta applied to pairs of objects. OI, OJ.
Whoa, okay, let's break that down. Fe dot theta, sum.
Yeah. Let's forget the Greek letters for a sec. Think of G theta as a little function, usually in MLP.
A multi-layer perceptron, like standard neural net layers.
Exactly. This G function looks at two objects at a time, say object I and object J, and its whole job is to figure out how they might be related, or even if they're related.
So it's like a pairwise relationship detector.
Precisely. Its output is what the paper calls a relation. Then that summation symbol just means you do this G calculation for every single possible pair of objects in your set O.
Every single pair. Uh-huh.
And finally, that IFE function, which is usually another MLP, takes all those individual relation outputs from G, sums them up, and then uses that combined information to make a final decision or prediction about the whole set.
Got it. So G looks at pairs, you sum up all those pairwise findings, and F makes sense of the total picture of relations.
You got it. That's the core mechanism.
Cool. The paper mentions three key strengths of this approach. The first one is about learning to infer relations.
Yeah, and this is really key. The RN, just by how it's built, looks at all possible pairs. It doesn't start with any clues about which pairs matter or what kind of relationship to look for.
Gee, it has to figure that out from the data.
Exactly. It learns to spot the relevant connections. The paper uses a nice analogy. Think of your objects as nodes in a graph, and the RN considers every possible directed edge between them.
Like a fully connected graph of potential relationships.
Pretty much. Now, they mostly use this all pairs approach, but they do mention you could adapt it to only look at specific pairs if you had some prior knowledge. But the default is check everything.
Interesting. Starting broad and narrowing down. Okay, second strength. Data efficiency. How does that work?
This is a big one. Remember that G function that checks the relationship between a pair?
Yeah, the pairwise detector.
The RN uses the exact same G function with the same learned parameters for every single pair it checks.
Ah, okay. So it learns one general relationship detector and applies it everywhere.
Right. Now, think about how a standard MLP might try to do this. You would kind of need to learn a separate way to compare each specific pair. If you have n objects, that's potentially n squared, different comparisons it needs to learn specifically.
That sounds like it would get out of hand really fast.
Totally intractable as n grows. The Rn does n squared calculations, sure, one for each pair, but it only has to learn that single g function.
Which means it should generalize better, right? Learning the concept of a relationship rather than just memorizing specific examples.
Exactly. It promotes generalization because that one function has to work across all sorts of different pairs.
That's clever. Okay, and the third strength, operating on a set of objects.
Yeah, that relates back to that summation step. Because you sum up the results from all the pairs, the final output doesn't depend on the order you listed the objects in initially.
Ah, order invariance. Because a set is a set no matter how you list the items.
Precisely. A red ball and a blue cube is the same set as a blue cube and a red ball. The Rn respects that property.
So the final output really reflects the relationships within the group, regardless of presentation order.
Which is what you usually want when you're reasoning about a whole scene or situation.
Okay, this gives us a really good picture of what RNs are and why they're designed this way. Now, the fun part, how did they actually do? Let's talk applications. First up was CLVR, right? Visual question answering.
Yep, CLVR. It's a dataset designed specifically to test reasoning about 3D objects in images. The questions often require understanding relationships, spatial ones, attribute comparisons, counting.
Like, is the small metal sphere behind the big rubber cube kind of stuff?
Exactly like that. Or how many objects are the same size as the cylinder. It forces the AI to look at multiple objects and their connections.
And why is CLVR considered a good benchmark?
Well, it's quite carefully constructed. It tries to avoid shortcuts, like models just guessing based on linguistic biases or needing tons of real-world knowledge. It focuses tightly on reasoning about the visual scene and the language of the question. CLEVR stands for Compositional Language and Elementary Visual Reasoning.
Compositional language, elementary visual reasoning. Got it. And standard models struggled with this.
They did, especially in the relational questions. The paper mentions models using things like ResNets for vision, LSTMs for the question, even attention mechanisms.
So pretty sophisticated stuff already.
Yeah, but on questions like comparing attributes or counting objects based on relationships, they often weren't much better than a baseline guesser.
So they could maybe see the objects but not reason about them effectively.
That seems to be the implication. They lack that core relational inference part. That's the gap the RN is supposed to fill.
Okay, so, drumroll. How did the RN augmented model do on CLVR?
The results were pretty stunning, honestly. The RN enhanced model got 95.5% accuracy on CLVR, learning directly from the image pixels.
95.5%. How does that compare?
It was state-of-the-art at the time. A huge jump, like 27% absolute improvement over the previous best pixel-based model. And get this, it was actually better than the reported human accuracy on the dataset.
Whoa, superhuman performance on a reasoning task.
Yeah, and specifically on those tough compare attribute and count questions, the improvement was massive. It really showed the RN was doing what it was designed for.
That's incredible. Just adding this RN module made that much difference.
Seems so. And the researchers also noted their RN model was arguably simpler, architecturally, than some of the other complex models that had been tried.
Simpler and better. Nice. Did they test it in other ways on CLER? You mentioned state descriptions.
Right. So besides feeding it raw pixels, they also tried giving it the object information more directly. Like, instead of an image, here's a list. Object 1 is a red cube at coordinates x, y, z. Object 2 is a blue sphere at Burien. You get the idea.
Okay, so bypassing the image perception part and just feeding it the facts.
Exactly. They wanted to see if the RN's reasoning power depended on having to figure out the objects from pixels, or if it worked well just given the descriptions.
Yeah.
It still performed incredibly well, 96.4% accuracy.
Wow. So the RN module itself is robust, whether it gets object features from a vision system or directly.
That's what it suggests. It's good at reasoning about the relationships, regardless of how it learned about the objects themselves. Hints at broader potential, maybe beyond just vision.
Definitely. Okay, next up was sort of CLVR. Sounds cute. What was the point of that one?
Yeah. It was a simplified, more controlled setup. The goal was to really isolate relational versus non-relational reasoning.
How'd they do that?
Very simple scenes, just 2D colored shapes.
Mm-hmm.
And the questions weren't natural language. They were hard-coded binary strings to remove language ambiguity.
Okay.
And crucially, they deliberately created pairs of questions for each scene. one relational, one not. Like a non-relational question might be, what shape is the red object?
Simple lookup.
Right. And a relational one might be, what shape is the object closest to the red object?
Yeah.
Or how many shapes are the same color as the blue one?
Ah, I see. A direct comparison. So what happened?
This was really telling. A standard CNN plus an RN got over 94% accuracy on both types of questions, relational and non-relational.
Okay. Handle both well.
But
Handle.
when they took out the RN and put in a standard MLP of similar complexity,
Yeah.
the CNN plus MLP did fine on the non-relational questions. But on the relational ones, it plateaued at around 63% accuracy. Couldn't get the hang of it.
Only 63%. That's a huge gap.
A massive gap. They specifically mentioned it struggled with closest to and furthest from relations. It just really drives home the point.
That you need something designed for relational reasoning to handle even simple relational tasks. The standard stuff just doesn't cut it.
Exactly. Couldn't have said it better.
Okay, moving from shapes to words. They also tested this on the Bobby I dataset for text QA. What's Bobby about?
Bobby is a set of 20 tasks. Each gives you a little story, like a few sentences of facts, and then asks a question that requires reasoning over those facts.
Like reading comprehension, but testing specific reasoning skills.
Pretty much. You might get, John picked up the ball. John went to the garden. Then the question, where is the ball? You have to connect the facts. Many memory-based networks do pretty well on Bobby I.
So how did the RN model stack up?
It did really well. Solved 18 out of the 20 tasks successfully.
18 out of 20, that's solid.
Yeah. And notably, it aced one called basic induction, which had apparently been tricky for other kinds of memory networks. And the two it failed weren't like total failures, just not perfect accuracy.
And they trained it on all tasks at once.
Yes, jointly trained on all 20 with a single set of parameters, which suggests it's learning a pretty general reasoning capability that works across different text scenarios.
Impressive. Visual reasoning, text reasoning.
Mm.
What else? Ah, dynamic physical systems. That sounds cool.
This one was neat. They simulated systems with, like, colored balls moving around. Some balls were connected by invisible springs or rods.
Invisible connections? Okay.
Yeah, so you just see the balls moving. The input was basically the coordinates and colors of each ball over time, like 16 frames.
And the tasks?
Two main ones. First, figure out which pairs of balls were connected by these invisible links. Second, count how many separate connected groups there were in total.
Okay, both sound like they'd need relational reasoning. You have to see how the ball's movements relate to each other over time.
Definitely.
Yeah.
Especially the counting task. It's implicit relational reasoning. You have to first figure out the connections to then count the groups.
Right. And the RN performance?
Really strong again.
Hmm.
93% accuracy on inferring the connections, 95% on counting the systems.
Wow. And how did a standard MLP do here?
Basically chance level. Couldn't figure it out at all, even with a similar number of parameters. Just noise.
That's a stark contrast. Really highlights the RN's ability to pick up on those dynamic physical relationships.
Absolutely. And there was one more kicker with this experiment.
Oh, yeah.
They tried applying the RN trained on these bouncing balls to a completely different data set. Motion capture data of a person walking.
Seriously. From simulated balls to human motion capture.
Yeah. It could actually predict the connections between the person's body joints reasonably well, even though it had never seen human motion data before.
That's amazing transfer learning. It suggests the RN learned something fundamental about inferring connections from motion, not just about the specific balls and springs setup.
Exactly. It implies a deeper understanding of relational patterns and dynamic systems.
Yeah.
Really exciting stuff.
Okay, wow. So let's try to wrap our heads around this. We've seen RNs excel in visual QA, simplified reasoning, text QA, and dynamic physics. What are the big takeaways here?
I think the main one is just how effective RNs seem to be as this general-purpose plug-and-play module for adding relational reasoning power to different kinds of neural networks.
It seems quite versatile.
Very. And it suggests this interesting idea, maybe some separation between perception or processing, like what CNNs or LSTMs are good at, and explicit reasoning, which is where RNs shine.
A division of labor in the network?
Kind of. Another key point is how RNs seem able to learn useful object-like representations in the relationships, even from raw data, like pixels or coordinates, without being explicitly told this is an object.
That ability to structure the input seems powerful.
Definitely. And it opens up doors for future work, right?
Yeah.
You can imagine using these in reinforcement learning agents to understand complex environments, or maybe for modeling social interactions or tackling abstract problems.
Yeah, lots of possibilities. Did the paper mention improving RNs themselves?
briefly. They touched on ideas like maybe using attention mechanisms within the RN, possibly to help it focus on the most relevant pairs instead of always checking every single one, could make them more efficient for really large numbers of objects.
Makes sense. Focus the reasoning power.
Right.
Okay, this has been a fantastic deep dive. Relation networks seem genuinely powerful and flexible for tackling that crucial aspect of intelligence understanding relationships.
Yeah, to sum it up, they offer this simple-ish yet really effective way to give neural nets that relational boost, leading to some pretty dramatic performance gains across surprisingly different areas.
So as we finish up, here's something for you, the listener, to think about. We've seen RNs work brilliantly in these controlled, somewhat clean data sets like CellAVR or the simulations. What do you think are the biggest challenges or hurdles to making similar relational reasoning modules work effectively on truly messy, complex, real-world problems?
Yeah. Where the data is noisy, maybe ambiguous. How do you even define what an object or a relation is in, say, a chaotic real-world video or a huge unstructured text document?
Yeah,
That seems like a big step.
it does. Lots to chew on there.
And hey, if you want to dig deeper into the experiments, especially the dynamic physics stuff, the paper actually has supplementary materials, including a YouTube link with videos. Seeing the simulations really helps visualize what the RN is doing. We'll point you towards that.
Definitely worth checking out. It's clear that figuring out relational reasoning is a major step forward for AI, and relation networks look like a really significant piece of that puzzle. Thanks for joining us for this deep dive.